The nearest star to our Sun is not a star. It is 3. This is the first surprise of Alpha Centauri, the system that has captured human imagination for centuries, the destination that appears in more science fiction stories than perhaps any other real astronomical object, the place that represents humanity's closest possible reach beyond our own solar system. When you look up at the southern sky and find the bright pair of stars that make up what navigators called Alpha Centauri, you are looking at a triple star system. 3 gravitationally bound suns orbiting each other in configurations that span an enormous range of scales, presenting a set of conditions unlike anything in our own solar system. And the third of these 3 stars, the one too faint to see without a telescope, the one not visible in the familiar bright pair, happens to be the closest individual star to the Sun, Proxima Centauri. At approximately 4.24 light-years away, it holds the distinction of being our nearest stellar neighbour by a comfortable margin. But close is a deeply misleading word in this context. 4.24 light-years. Let that settle for a moment. Light travels at approximately 299,792 kilometers per second. In 1 year, it covers about 9.46 trillion kilometers. Proxima Centauri is 4.24 of those years away, approximately 40 trillion kilometers, about 268,000 times the distance from Earth to the Sun. The fastest human-made object ever launched, the Parker Solar Probe, at its closest approach to the Sun, reaches speeds of roughly 690,000 kilometers per hour. At that speed, reaching Proxima Centauri would take approximately 6,300 years. This is the true scale of Alpha Centauri, not the poetic distance of a nearby star, not the comforting proximity implied by the phrase nearest neighbour, a distance so vast that the fastest machines humans have ever built would require more than 60 centuries to cross it. Tonight we are going to examine this system honestly, its structure, its scale, its complexity, and what the presence of 3 stars rather than 1 fundamentally changes about everything we might ever hope to do there. We will follow the physics and the numbers carefully, without softening the implications, because the Alpha Centauri system is both one of the most fascinating objects in the sky and one of the most humbling demonstrations of the scale of the universe we inhabit. If the night is long, stay. The story of Alpha Centauri is one of the most layered in stellar astronomy, and it changes substantially the moment you understand that what looks like 1 or 2 stars is actually 3. Let us start with the history of how we know what we know. For most of human history, Alpha Centauri was simply a bright star in the southern sky, the 3rd brightest star in the entire night sky as seen from Earth, after Sirius and Canopus. It was known to ancient cultures in the southern hemisphere for millennia. It was used for navigation. It has mythological significance in multiple southern hemisphere cultures. The binary nature of the system, the fact that the bright object in the sky is actually 2 stars rather than 1, was first recognized by European astronomers in the 18th century. Jean Fichot, a French Jesuit priest observing from Pondicherry in India, noted in 1689 that Alpha Centauri appeared to be a double star. Subsequent observations confirmed this. The 2 bright components, now designated Alpha Centauri A and Alpha Centauri B, orbit each other in an elliptical orbit with a period of approximately 79.9 years. The parallax distance to Alpha Centauri was first measured in the 19th century. Thomas Henderson, a Scottish astronomer working at the Cape of Good Hope in South Africa, made the first measurements in 1832 and 1833, though he was cautious about publishing them and was beaten to the honour of announcing the first stellar parallax measurement by Friedrich Bessel, who measured the distance to 61 Cygni in 1838. Henderson eventually published his Alpha Centauri measurements in 1839, placing it at approximately the correct distance. This measurement, the first reasonable estimate of the distance to the nearest star, was a landmark in human understanding of the cosmos. Before stellar parallax measurements, it was known that the stars were very far away, but the scale was essentially unknown. The measurement of Alpha Centauri's distance revealed for the first time a specific number, approximately 4 light-years, for the gulf between our Sun and its nearest neighbour. The enormity of even this nearest stellar distance was immediately apparent. Proxima Centauri, the third member of the system and the actual closest star to the Sun, was not discovered until 1915 by Scottish-South African astronomer Robert Innes, working at the Union Observatory in Johannesburg. It was identified as a separate faint red star whose proper motion, its angular movement across the sky relative to the background stars, matched that of Alpha Centauri A and B, suggesting it was associated with the system. Subsequent measurements confirmed both its proximity, making it closer to Earth than the A and B components at the time of discovery, and its probable gravitational association with the Alpha Centauri AB binary. The discovery of Proxima added a third dimension to the system. It was not simply a nearby binary, but a triple system, 2 bright Sun-like stars in a close binary orbit, with a third, much dimmer red dwarf at an enormous distance from the central pair. Let us now talk about the structure of the system in detail, because understanding the architecture of Alpha Centauri requires grasping 3 different scales simultaneously. Alpha Centauri A and B are what astronomers call a visual binary, 2 stars close enough to each other and to us that they can be seen as separate objects through a modest telescope, and whose orbital motion can be tracked over years and decades. Alpha Centauri A is the larger of the 2. It is a G-type main sequence star, the same class as our Sun. Its mass is approximately 1.1 solar masses, about 10% more massive than the Sun. Its luminosity is about 1.519 times the Sun's. It is somewhat brighter. Its surface temperature is about 5,790 Kelvin, almost identical to the Sun's 5,778 Kelvin. In most fundamental respects, Alpha Centauri A is the closest thing to a twin of our Sun known in the cosmos. If you replaced our Sun with Alpha Centauri A, the differences in the solar system would be modest. Slightly brighter days, slightly warmer surfaces, a slightly different ultraviolet environment, but within the range that Earth-like planets could comfortably accommodate. Alpha Centauri B is the smaller of the 2 central stars. It is a K-type main sequence star, slightly smaller, cooler, and dimmer than the Sun. Its mass is approximately 0.9 solar masses. Its luminosity is about 0.5 solar luminosities, roughly half as bright as the Sun. Its surface temperature is about 5,260 Kelvin, noticeably cooler than the Sun's. K-type stars like Alpha Centauri B are considered excellent candidates for hosting habitable planets because they are more stable than larger stars, producing less ultraviolet radiation, while being bright enough to provide sufficient energy for a habitable zone that is not too close to the star. The orbit of Alpha Centauri A and B around each other is elliptical, significantly elongated rather than circular. The orbital period is approximately 79.9 years. The separation between the 2 stars varies substantially over this orbit, from a minimum of approximately 11.2 astronomical units at the closest approach, called periastron, to a maximum of approximately 35.6 astronomical units at the farthest separation, called apastron. For context, 11.2 astronomical units is roughly the distance from the Sun to Saturn. 35.6 astronomical units is slightly beyond the orbit of Neptune. So at their closest, Alpha Centauri A and B are separated by about the Sun-Saturn distance. At their farthest, they are separated by slightly more than the Sun-Neptune distance. This varying separation has profound implications for any planets that might orbit either star. We will return to this. Now let us scale out dramatically to consider Proxima Centauri. Proxima Centauri is currently located at a distance of approximately 12,950 to 13,000 astronomical units from the Alpha Centauri AB binary, roughly 2.2 trillion kilometers from its two larger companions. At this distance, Proxima is barely gravitationally bound to the AB binary. It is the most loosely attached member of the system, requiring an enormous orbit to complete one circuit around the central pair. The orbital period of Proxima around the AB binary is estimated at roughly 550,000 years. Think about that number for a moment. While Alpha Centauri A and B complete one orbit around each other in 79.9 years, a human-scaled timescale less than a human lifetime, Proxima completes one orbit around both of them in approximately 550,000 years. More than 500,000 years for one circuit. The Roman Empire rose and fell in less than a tenth of the time it takes Proxima to complete one loop around its companions. And the distance, 13,000 astronomical units. The orbit of Pluto around the Sun is about 40 astronomical units. Proxima orbits the AB binary at 325 times Pluto's orbital distance from the Sun. If you scaled the AB binary to the size of a basketball and placed it in the center of a city, Proxima at the same scale would be roughly 200 kilometers away, in another city entirely. This is the architecture of Alpha Centauri, a tight inner binary of two solar-type stars orbiting each other on an 80-year ellipse, with a third tiny red dwarf at an unimaginable distance orbiting the pair on a 500,000-year orbit. These three stars define three completely different scale regimes in a single gravitationally bound system. Let us now talk about Proxima Centauri in more detail. Because it is the closest star to the Sun, it is the most studied of the three, and its properties are in many ways the most surprising. Proxima Centauri is a red dwarf, an M-type main sequence star, the most common type of star in the galaxy. Approximately 70% of all stars are M-dwarfs. Despite this numerical dominance, no M-dwarf star is visible to the naked eye from Earth. They are too dim. Proxima Centauri itself, at a magnitude of about 11.1, requires a telescope of at least 100 mm aperture under good conditions to detect visually. Proxima's mass is about 0.122 solar masses, roughly 12% of the Sun's mass. Its radius is about 0.145 solar radii, roughly 15% of the Sun's diameter. Its luminosity is approximately 0.0017 solar luminosities, about 0.17% of the Sun's light output. It is an extremely dim, extremely small star. But Proxima Centauri's diminutiveness is not the most interesting thing about it. What makes it fascinating is its extreme longevity and its behavior. A star's lifetime on the main sequence, the period during which it fuses hydrogen in its core and remains in stable equilibrium, is roughly inversely proportional to the square of its mass. The Sun will spend about 10 billion years on the main sequence total, of which roughly 4.6 billion have already elapsed. Proxima Centauri, with its much lower mass and much slower rate of hydrogen consumption, will spend approximately 4 trillion years on the main sequence. 4 trillion years. The current age of the universe is approximately 13.8 billion years. Proxima will continue fusing hydrogen for roughly 290 times the current age of the universe before it exhausts its hydrogen fuel. This extraordinary longevity has implications for potential life. If there are planets around Proxima Centauri, and we know there is at least one and possibly more, those planets have been available for the development of life for approximately 4.8 billion years already, and will continue to be available for trillions of years more. The timescale available for life to develop and evolve around Proxima is vastly larger than it is around any Sun-like star. But Proxima's longevity comes with a cost. Red dwarfs are known for their intense stellar activity, particularly their tendency to produce powerful flares. Proxima Centauri is a flare star. It regularly emits intense bursts of ultraviolet and X-ray radiation that, relative to the star's normal output, are far more powerful than solar flares relative to the Sun's normal output. These flares are significant for the habitability of any planets in Proxima's system. A planet in the habitable zone of Proxima, the range of distances where liquid surface water could exist, orbits at roughly 0.05 astronomical units from the star. This is about 1/20th of the Earth-Sun distance, much closer than Mercury is to our Sun. At this close distance, even a modest flare from Proxima delivers a substantial radiation pulse to the planet's surface. Proxima b, the planet discovered orbiting Proxima Centauri in 2016, orbits at approximately 0.0485 astronomical units, with a period of roughly 11.2 days. Its minimum mass is about 1.07 Earth masses. It could be a rocky planet similar in size to Earth. Whether it is actually habitable depends on factors we do not yet know. Whether it has a substantial atmosphere, whether that atmosphere has survived billions of years of Proxima's flare activity, whether it has liquid water on its surface. The flare issue is not trivially solvable. Proxima's flares strip away planetary atmospheres over time through a process called atmospheric erosion. The energetic particles of the stellar wind and the intense UV and X-ray radiation ionize the top of the atmosphere and give atoms enough energy to escape into space. Whether Proxima b has retained sufficient atmosphere for habitability, despite billions of years of this erosion, depends on whether the planet had a sufficiently strong magnetic field to deflect the stellar wind and protect the atmosphere. This is one of the most actively debated questions in astrobiology regarding Proxima b. We do not know the answer. We cannot determine it from current observations. The next generation of instruments, particularly the European Extremely Large Telescope, currently under construction in Chile, may be able to detect Proxima b's atmosphere spectroscopically, if it has one. Let us now talk about the planetary systems of Alpha Centauri more broadly, about what we know, what we suspect, and what the gravitational environment of a triple star system means for planet formation and stability. Planet formation around single stars is now reasonably well understood at a qualitative level. A protoplanetary disk of gas and dust forms around the young star. Particles in the disk collide and stick together, forming planetesimals. Planetesimals accrete into protoplanets. Protoplanets grow into planets, and the disk is eventually cleared by the young star's radiation and stellar wind. Around a binary star system like Alpha Centauri AB, planet formation faces additional constraints. The gravitational influence of the companion star imposes a tidal perturbation on the disk that tends to heat and stir the disk material. This stirring increases the relative velocities of particles and planetesimals. Instead of gently colliding and sticking together, they collide at higher velocities and can instead fragment rather than accrete. This effect potentially suppresses planet formation in certain regions around each star. The region where planets can form stable, long-term orbits around a single star in a binary system, called the S-type or circumstellar orbital zone, is limited. Roughly speaking, stable circumstellar orbits around Alpha Centauri A are possible out to approximately 2 to 3 astronomical units from A, with the exact limit depending on the orbital phase of the AB binary and other factors. Similarly for Alpha Centauri B. Beyond this limit, in the region between the two stars, orbits are dynamically unstable and planets cannot survive long-term. There is also a third class of orbit, circumbinary or P-type orbits, where a planet orbits both stars simultaneously from a large distance. For Alpha Centauri AB, stable circumbinary orbits would need to be outside roughly 5 to 10 times the maximum separation of the two stars, that is, outside roughly 180 to 360 astronomical units. At such distances, any planet would be frigidly cold and far from any conceivable habitable zone. This orbital architecture significantly limits where habitable planets could exist around the Alpha Centauri AB binary. The habitable zone of Alpha Centauri A, the range of distances where liquid water could exist on a planetary surface, is roughly 1.0 to 1.4 astronomical units, broadly similar to Earth's distance from the Sun. For Alpha Centauri B, the habitable zone is at roughly 0.7 to 1.0 astronomical units. Both habitable zones fall within the region where S-type orbits can be stable. So planets in the habitable zones of both stars are at least dynamically possible. Whether planets actually formed there is a different question. The detection of planets around Alpha Centauri A and B has been a challenging observational problem. In 2012, a paper reported the detection of a planet around Alpha Centauri B, designated Alpha Centauri BB, with a minimum mass of about 1.1 Earth masses and an orbital period of about 3.2 days, placing it extremely close to the star and far too hot to be habitable. This detection was subsequently disputed, and the planet is no longer considered confirmed. The original signal appears to have been an artifact of the data analysis method. As of current knowledge, no confirmed planets around Alpha Centauri A or B exist. The search continues with advanced radio velocity instruments and with direct imaging techniques, but the nearby binary nature of the system makes planet detection there particularly difficult. The stellar activity of both stars produces signals that can mimic the gravitational tug of a planet, complicating the analysis. The search for planets around the Alpha Centauri system is one of the most active and technically challenging programs in exoplanet science. The scientific motivation is obvious. If Earth-like planets exist in the habitable zones of A or B, they would be the closest potentially habitable worlds known outside our solar system. Let us talk about why the detection of planets around Alpha Centauri A and B is so technically difficult, because understanding the challenge clarifies both the current state of knowledge and what future instruments might achieve. The primary method used to detect planets around nearby stars is the radial velocity technique, also called the Doppler spectroscopy method. When a planet orbits a star, the planet's gravity causes the star to move in a small orbit around the system's center of mass. This motion causes the star's light to be periodically Doppler shifted, stretched to redder wavelengths when the star moves away from us, compressed to bluer wavelengths when it moves toward us. By measuring these tiny wavelength shifts with extreme precision, astronomers can infer the presence of a planet and estimate its mass and orbital period. The technique is extraordinarily powerful. The most sensitive instruments can detect radial velocity variations of less than 1 meter per second, essentially the walking speed of a human being applied to a star millions of times more massive. But for Alpha Centauri A and B, the challenge is compounded by several factors. First, the binary nature of the system means the radial velocity of each star contains a large signal from its companion. The orbital motion of A and B around each other produces radial velocity variations of hundreds of meters per second, many orders of magnitude larger than the tiny signals expected from Earth-mass planets. This large binary signal must be modelled and subtracted with extreme precision before the residual can be searched for planetary signals. Any imperfection in the binary model contaminates the residual and can either produce false detections or mask real ones. The 2012 Alpha Centauri BB detection appears to have suffered exactly this problem. The subtraction of the binary signal was imperfect in a subtle way, and the residual signal, interpreted as a planet, was actually an artifact of that subtraction. This is not a failing of the specific researchers who made the detection. It illustrates the fundamental difficulty of the problem. Extracting a signal smaller than 1 meter per second from data dominated by signals hundreds of meters per second larger requires extraordinary care and is susceptible to systematic errors that are very difficult to identify. Second, the intrinsic stellar activity of both stars, sunspot-like magnetic activity features on the stellar surface, produces quasi-periodic radial velocity variations that can mimic planetary signals. Stars are not perfectly uniform radiating spheres. Active regions on the stellar surface rotate with the star, periodically altering the apparent radial velocity through the line profile variations they produce in the stellar spectrum. These stellar activity signals must also be modelled and removed, adding another layer of uncertainty. The combination of the binary signal subtraction problem and the stellar activity problem makes the Alpha Centauri AB system one of the most challenging targets for radial velocity planet searches, despite its proximity. Dedicated instruments designed specifically for this challenge have been deployed. The HARPS spectrograph at the La Silla Observatory in Chile has been used extensively. The Espresso spectrograph at the Very Large Telescope, one of the most precise radial velocity instruments ever built, has been applied to the system. Both have provided valuable constraints, but neither has yielded a confirmed planet detection around A or B. Direct imaging is another approach, literally taking a photograph of a planet orbiting one of the stars, rather than inferring its presence from its gravitational effect on the star. The challenge with direct imaging is the extraordinary contrast between a star and any orbiting planet. A star is typically billions to tens of billions of times brighter than a planet at visible wavelengths. Separating the faint light of a planet from the overwhelming glare of its host star requires coronagraphs that block the starlight and adaptive optics systems that correct for atmospheric blurring. The proximity of Alpha Centauri is both an advantage and a disadvantage for direct imaging. The advantage is angular resolution. A given physical separation around Alpha Centauri corresponds to a larger angle on the sky than the same separation around a more distant star, making the planet-star separation easier to resolve. The disadvantage is the binary nature. The two stars in the AB pair are close enough to each other on the sky that imaging around each individual star is complicated by the presence of the other. Future space-based coronagraph missions, particularly the Nancy Grace Roman Space Telescope, which has coronagraph technology on board, may be able to image Jupiter-sized planets around Alpha Centauri. The Habitable Worlds Observatory, a proposed future flagship telescope, is designed with sufficient coronagraphic capability to potentially image Earth-sized planets in the habitable zones of nearby stars. including the Alpha Centauri system. This mission, if built, would represent the most direct approach to answering the question of habitable planets around Alpha Centauri A and B. Let us now talk about what 3 stars, rather than 1, means for the light environment of any planets in the system, because this is one of the most visually distinctive and physically significant aspects of the Alpha Centauri triple system. Imagine a planet orbiting Alpha Centauri A at roughly Earth's distance from the Sun. From this planet, Alpha Centauri A would appear as a brilliant star, somewhat brighter than our Sun appears from Earth, because Alpha Centauri A is slightly more luminous. This star would provide the daylight, drive the weather, and define the rhythm of days and seasons. But the sky of this planet would contain additional stellar companions that our sky does not. Alpha Centauri B, orbiting A at a separation that varies from 11 to 36 astronomical units, would appear as an extremely bright star in the sky, at its closest approach appearing with an apparent brightness of roughly magnitude -19 to -20. For reference, our full moon has an apparent magnitude of roughly -12.7. Alpha Centauri B at closest approach from a planet around A would appear roughly 60 to 600 times brighter than our full moon, depending on exact geometry. This is extraordinarily bright, bright enough to cast distinct shadows on a clear night, bright enough to be visible in daylight as a brilliant point of light, bright enough to significantly contribute to nighttime illumination and to affect the biological rhythms of any organisms adapted to a day-night cycle. It would be a permanent feature of the sky, not rising and setting like a moon, but shifting slowly in position as the years pass, growing brighter as the AB binary approaches periastron, and dimmer as it recedes toward apastron. At apastron, maximum separation, Alpha Centauri B would appear dimmer, roughly the brightness of Venus at its brightest, as seen from Earth, but still an unusual and striking feature of the night sky. Proxima Centauri, at its distance of 13,000 astronomical units from the AB pair, would be invisible to the naked eye from any planet in the Alpha Centauri AB system, too faint, too distant, indistinguishable from the background stars. Its gravitational influence on a planet around Alpha Centauri A would be negligible. Now consider the reverse, a planet orbiting Proxima Centauri. From Proxima B or any other planet around Proxima, the night sky would contain Alpha Centauri AB as a brilliant double star. The 2 stars close enough together in the sky to appear as a single, very bright point to the naked eye, or resolvable into a distinct pair with moderate optical aid. At their combined apparent brightness from Proxima's distance of 13,000 astronomical units, the Alpha Centauri AB system would appear at roughly apparent magnitude -6.5, more than 100 times brighter than Venus at its brightest as seen from Earth, bright enough to cast shadows, clearly visible in a daytime sky. Any beings on a planet around Proxima Centauri would have grown up under a night sky dominated by a brilliant double star, the 2 suns of the Alpha Centauri AB system blazing together in their sky. The mythology, the navigation, the entire cultural relationship with the stars of such a civilization would be shaped by the presence of these 2 brilliant companions at their corner of the cosmos. This is one of the most evocative aspects of the Alpha Centauri system, the reciprocal illumination of its members. From one part of the system, you see the other, brilliantly. The 3 stars light each other's skies in ways that have no parallel for planets in our solar system. Let us now talk about the long-term dynamical future of the Alpha Centauri system. because the three-star architecture has implications not just for the present, but for how the system will evolve over billions of years. The AB binary is in a stable configuration, two stars of comparable mass in a bound elliptical orbit. Barring interaction with a passing star or other perturbation, this configuration will persist for billions of years. The orbit will evolve slowly through gravitational radiation, the emission of energy in the form of gravitational waves. But at the AB pair's separation and mass, this effect is negligibly small. The binary will remain essentially unchanged on astronomical timescales. Proxima's association with the AB binary is more precarious. Its orbit around the AB pair is so wide and its binding energy so low that interactions with passing field stars, which occur frequently on the long timescales of stellar evolution, could potentially perturb Proxima enough to unbind it from the system. There is genuine uncertainty among astronomers about whether Proxima is truly gravitationally bound to Alpha Centauri AB, or is simply a passing star that happens to be moving through the same region of space. The evidence for physical association is primarily the close match in proper motion. Both the AB pair and Proxima are moving through space at essentially the same velocity in the same direction, which would be a remarkable coincidence if they were unrelated. The radial velocities also match closely. The probability that this match is coincidental rather than reflecting a common origin and gravitational binding is estimated to be very small, perhaps less than 1 in 200,000. But the binding itself is marginal. Gravitational simulations of Proxima's orbit in the realistic galactic environment, including the gravitational perturbations of passing stars and the overall galactic gravitational field, suggest that Proxima may have been captured by the Alpha Centauri AB system rather than having formed alongside it, and that its orbit is loosely enough bound that it may eventually escape on timescales of tens to hundreds of billions of years. The stellar evolution of the individual stars also matters for the long-term future. Alpha Centauri A, being slightly more massive than the Sun, will exhaust its hydrogen fuel somewhat sooner than the Sun, in roughly 5 to 6 billion years from now, compared to the Sun's remaining 5 billion years. When A exhausts its hydrogen, it will expand into a red giant, dramatically increasing its luminosity. This will temporarily shift the habitable zone of Alpha Centauri A outward, and then destroy any inner planets as A's envelope expands. Alpha Centauri B, being slightly less massive, will remain on the main sequence somewhat longer, perhaps 12 to 14 billion years total from its formation, meaning it has several billion years remaining. Proxima Centauri, as we discussed, has approximately 4 trillion years remaining on the main sequence, essentially forever on the scale of any timescale that is meaningful for stars and planets. So the 3 stars of Alpha Centauri will evolve on 3 completely different timescales. Proxima will still be quietly fusing hydrogen long after the A and B components have exhausted their fuel, evolved off the main sequence, and cooled to white dwarfs. By the time Proxima has burned through even a small fraction of its fuel, the A and B stars will be cold remnants. The system that looks like a unified triple at the current moment of cosmic time is therefore in a very particular phase. We are observing it at a time when all 3 components are main sequence stars, a coincidence of timing that will not persist on astronomical timescales. Let us now talk about the interstellar travel implications of the Alpha Centauri system, because this is where the system's significance for humanity's long-term future becomes most explicit. Alpha Centauri is the target of the most seriously discussed interstellar travel concepts in the scientific and engineering literature. The Breakthrough Starshot initiative, funded by Yuri Milner and announced in 2016, proposed sending a fleet of gram-scale laser-pushed light sails to Alpha Centauri at roughly 20% of the speed of light. At this speed, the journey would take approximately 20 years. This is technically ambitious to the point of requiring multiple significant engineering breakthroughs. The laser array needed to push the light sails, operating at power levels of roughly 100 gigawatts focused on each sail, would be the most powerful laser system ever built by an enormous margin. The light sails themselves would need to be reflective to a degree not achieved by any material. The sensors and communication systems on a gram-scale spacecraft would need to be revolutionary. The deceleration problem, slowing down at Alpha Centauri, has no solution in the Starshot proposal. The tiny spacecraft would simply fly through the system at 20% of the speed of light, having only a brief window of hours to make observations. Despite these enormous challenges, breakthrough Starshot has motivated serious engineering and physics research into the underlying problems. Progress has been made on laser sail dynamics, on miniaturized electronics capable of surviving the interstellar environment, on sail material research. None of the fundamental challenges has been solved, but none has been proven impossible. For crewed missions, which would require carrying humans across 4.24 light-years at survivable accelerations, the challenges are vastly greater. Achieving even 10% of the speed of light with a crewed vessel would require energy inputs comparable to the entire current energy output of human civilization, sustained for years. The mass of fuel or energy storage required by any known propulsion method is orders of magnitude beyond anything buildable with conceivable extensions of current technology. Theoretical propulsion concepts that could potentially make crewed interstellar travel feasible, fusion drives using helium-3 or deuterium fuel, antimatter rockets, solar sails driven by focused laser arrays, magnetic sails, each face fundamental challenges either in fuel availability, engineering complexity, or physics that remains speculative. The honest assessment of human interstellar travel to Alpha Centauri is that it is not feasible with current technology. It is not clearly feasible with any technology we can reliably extrapolate from current understanding, and it would require advances in physics and engineering that we cannot confidently predict. This is not a statement that it will never happen. History is full of technologies that seemed impossible from the perspective of earlier eras. But it is a statement that the 4.24 light-year distance to Proxima Centauri, the nearest of the three stars, is not a manageable engineering challenge with anything we currently know how to build or with high confidence know how to design. The scale of Alpha Centauri is a scale that exposes the limits of current human capability in one of the most direct and concrete ways possible. Let us talk about what the system looks like from Earth in specific observational terms, about how to find it, what you can see, and what the act of observing it represents. Alpha Centauri is not visible from most of the northern hemisphere. From latitudes north of approximately 29 degrees north, which includes most of the continental United States, Europe, and most of Asia, Alpha Centauri never rises above the horizon. From the southern United States, the southernmost parts of Europe, and similar latitudes, it briefly appears very low on the southern horizon during certain times of year, but never rises high enough for convenient observation. From the southern hemisphere, from Australia, New Zealand, South Africa, South America, and southern latitudes generally, Alpha Centauri is one of the most prominent stars in the sky. It is the brightest star in the constellation Centaurus, and it reaches its highest point in the sky, at a comfortable altitude from most southern hemisphere locations. The two components of the AB binary, Alpha Centauri A and B, are currently separated by about 5 to 6 arc-seconds in the sky, a separation that has been decreasing as the binary moves toward periastron. At this separation, they are easily resolved in any small telescope, a 60 or 70 mm refractor at 50 times magnification, will cleanly separate the two stars into a beautiful pair. The colour difference is subtly visible in good telescopes. Alpha Centauri A is slightly warmer and appears slightly whiter, while Alpha Centauri B is slightly cooler and appears slightly more yellow or orange. Proxima Centauri is not visible without a telescope. It requires at least a 100 mm aperture under good conditions, and knowledge of its precise location is necessary to distinguish it from the background stars. It appears as a faint reddish star, very slightly red compared to its surroundings, consistent with its M-dwarf spectral type. The separation between Proxima Centauri and the Alpha Centauri AB binary on the sky is currently about 2.2 degrees, roughly 4 times the apparent diameter of the full moon. This means all 3 stars fit within a binocular field of view. You can see the bright pair, and then, if you know where to look, the faint reddish point of Proxima at 2.2 degrees away. The proper motion of the Alpha Centauri system, its angular movement across the sky relative to the background stars, is roughly 3.7 arcseconds per year. This is large by stellar standards, one of the largest proper motions of any bright star. Over a human lifetime, Alpha Centauri moves about 3 arc-minutes across the sky, a tenth of a full moon diameter, a motion detectable by comparing historical observations with current ones. This proper motion means that Alpha Centauri is not at its closest to the Sun right now. It is approaching. About 27,000 years from now, Alpha Centauri will reach its closest point to our solar system, at a distance of roughly 3.17 light-years, rather than the current 4.24. It will then move away again as the geometry of stellar motions in the galaxy carries it to greater distances over the subsequent hundreds of thousands of years. The nearest star is getting nearer. For the next 27 millennia, the distance to our closest stellar neighbour is decreasing by roughly 0.0017 light-years per millennium, approximately 16 billion kilometres per 1,000 years. It will eventually be closer than it is now. Then it will recede. On the timescale of galactic dynamics, neighbouring stars approach and recede as the orbital motions of stars around the galactic centre carry them through different configurations. Let us now talk about what the significance of the triple star architecture means for any intelligent civilization that might exist in the system, whether around Proxima b or around a hypothetical planet in the habitable zone of A or B. A civilization that evolved around Alpha Centauri A would have grown up with a sky containing a brilliant companion star, Alpha Centauri B, shining in their night sky with a brightness far exceeding our moon. Their astronomical history would have been different from ours. The binary nature of their star system would have been immediately obvious. Their primary star has a companion bright enough to be unmistakable, bright enough to affect tides, bright enough to be culturally significant in any society that looks at the sky. Their understanding of their own sun would have developed in the context of knowing that another star exists very close by. Their stellar astronomy would have begun not with the question, what are those distant points of light, but with, what is that second brilliant light that moves slowly through our sky? The concept of a binary star, 2 gravitationally bound suns, would have been immediate, obvious, and personally relevant, rather than an abstraction discovered through telescopic observation. Their physics, if they developed physics, would have had stellar mechanics as a first-hand observable. They could watch, over the course of a few human generations, the separation between their sun and its companion change as the 2 stars move through their 79.9-year orbit. They could measure the masses of both stars through the dynamics of that orbit, using Newtonian mechanics once they developed it. The gravitational constant, the laws of orbital mechanics, the mass-luminosity relationship, all testable in a direct, nearby laboratory visible to the naked eye. Proxima Centauri, from the perspective of this civilization, would be an extremely faint star, requiring telescopic observation, as unremarkable in their sky as any other dim red dwarf. Its status as the third member of their stellar system would only become clear after they developed precise astrometry capable of measuring proper motions of faint stars. A civilization that evolved around Proxima Centauri would have a very different astronomical perspective. Their primary star would be a dim red dwarf, providing much less light than our Sun provides Earth. Their planet would need to orbit very close to Proxima to be warm enough, meaning it would likely be tidally locked, one hemisphere always facing the star, one hemisphere always in darkness. The day side would be permanently lit by the red glow of a dim sun. The night side would be in permanent darkness. The terminator zone, the region between permanent day and permanent night, might be the most comfortable habitation zone. And in their night sky, perpetually visible from the night hemisphere and from the terminator, would shine the brilliant double star of Alpha Centauri A/B. Two stars so close together that they might appear to the naked eye as a single brilliant object, or might be resolvable as a close pair to keen observers. Their combined light would dominate the night sky, far beyond any other stellar object. This neighbouring double star would have been an object of fascination for any intelligent civilization around Proxima. Close enough to be spectacularly bright, demonstrably stellar in nature through its own colour and light quality, clearly moving slowly against the background stars as both systems execute their long orbital dance through the galaxy. The first astronomers of such a civilization would have known immediately that their sky is dominated by a nearby stellar pair. Their entire conception of the structure of the cosmos would have incorporated the existence of multiple star systems from the beginning. This thought experiment is not idle speculation. It illustrates something important about the relationship between environment and cognition. The questions intelligent beings ask about the universe are shaped by what they can see from where they are. A civilization around Proxima would ask different first questions about astronomy than we did. Their answers, if their physics is the same physics as it must be in a universe governed by universal laws, would be the same answers. But the path to those answers would be different. And the knowledge that we and any Proxima civilization share the same neighborhood, that Alpha Centauri A/B shines brilliantly in their sky, while our Sun, the bright component of their nearest stellar system, shines brilliantly in ours, would be among the most profound facts of any first contact with such a civilization. Let us now talk about what the current observational programs focused on Alpha Centauri are actually doing right now, about the specific scientific work in progress that is advancing our understanding of this system. Several dedicated programs are actively searching for planets around Alpha Centauri A and B. The most significant is the Ptolemon mission, a small space telescope whose name is taken from a historical Arabic name for Alpha Centauri, and which is an acronym for Telescope for Orbital Locus Interferometric Monitoring of our Astronomical Neighbourhood. Ptolemon is designed to detect planets around A and B using the astrometric method, measuring the tiny wobble of the star's position on the sky caused by an orbiting planet, rather than the radial velocity method. This approach avoids some of the systematic issues that have complicated radial velocity searches of the binary. Ptolemon was designed at the University of Sydney and represents a purpose-built instrument for this specific problem. Its design demonstrates the scientific seriousness with which the Alpha Centauri planetary search is now being conducted, dedicated instruments designed around the specific challenges of this specific system. The European Southern Observatory's espresso spectrograph continues radial velocity monitoring of both A and B with the precision needed to potentially detect Earth-mass planets in habitable zones. Espresso is the most precise radial velocity spectrograph currently operating, capable of detecting velocity changes of less than 30 centimeters per second, comparable to the speed of a slow-walking human. Imaging programs using adaptive optics on large ground-based telescopes continue to search for any giant planets on wider orbits around either star. While the habitable zones of A and B are too close to the stars for current coronagraphic imaging to resolve, larger planets at wider separations could potentially be detected. The combined program of radial velocity monitoring, astrometry, and direct imaging represents a comprehensive observational assault on the question of planets in the Alpha Centauri AB system. If Earth-mass planets exist in the habitable zones of these stars, the next decade's observations have a reasonable chance of detecting them. The Proxima Centauri system is simultaneously being studied through the most sensitive available instruments to characterize the known planet Proxima b and search for additional planets. Hints of a second planet, potentially Proxima c, on a wider orbit have been reported in some datasets, but this candidate is not yet confirmed. A confirmed multi-planet system around Proxima would be an extremely significant finding for understanding planet formation around red dwarfs. The atmospheric characterization of Proxima b, determining whether it has a substantial atmosphere, and if so, what it is made of, is a scientific goal for the next generation of instruments. The European Extremely Large Telescope, with its 39-meter primary mirror, may be capable of detecting Proxima b's atmosphere in reflected starlight. This would be one of the most significant observations in the history of exoplanet science, the first atmospheric characterization of the nearest potentially habitable exoplanet. The combination of all these programs means that within the next decade, perhaps by 2030 to 2035, we may know substantially more about the planetary systems of Alpha Centauri than we currently do. We may know whether A and B have Earth-mass planets in their habitable zones. We may know whether Proxima b has a significant atmosphere. We may know the masses and orbits of additional planets around all three stars. This knowledge will not make Alpha Centauri reachable. The distance remains what it is. But it will determine whether the nearest stellar system to our Sun contains worlds that could harbour life. Worlds that, however unreachable they are on any human engineering timescale, are neighbours in the deepest cosmic sense. Let us talk about what the scale of Alpha Centauri means in terms of light travel time. Because light travel time is in some ways the most physically meaningful way to understand the distances involved, and it connects the system to questions about information, communication, and the ultimate limits of any contact between civilizations. When you look at Alpha Centauri tonight, the light entering your eyes left those stars 4.24 years ago, or 4.37 years ago for the AB pair, which is slightly more distant than Proxima. The stars you are seeing are not the stars as they are now. They are the stars as they were in the recent past, a past separated from the present by slightly more than 4 years. This 4-year light travel time has a profound practical implication for any communication with the system. If we sent a radio message to Alpha Centauri today, a message travelling at the speed of light, the fastest possible transmission, the message would arrive at the system in approximately 4.24 years. Any response, also travelling at the speed of light, would return to Earth in another 4.24 years. The minimum round-trip communication time is roughly 8.5 years. This is not an engineering limitation. It is not something we could overcome with more powerful transmitters or better receivers. It is a consequence of the finite speed of light, a fundamental physical constant, and the physical distance between our solar system and Alpha Centauri. No communication technology can exceed the speed of light. The 8.5-year round-trip time is irreducible. For any kind of interaction between two civilizations, one around the Sun and one around Alpha Centauri, this communication delay fundamentally changes the character of the interaction. A conversation in any meaningful sense is impossible. You cannot ask a question and receive an answer in a back-and-forth dialogue. What is possible is the exchange of messages, each side sending information into the void and receiving responses after delays measured in years. This is very different from interplanetary communication within our solar system, where even the Sun-Mars round trip is at most 44 minutes, but still fundamentally different from interstellar distances further out. At Alpha Centauri's 4.24 light-years, we are in the regime of years rather than decades or centuries. A civilization at Alpha Centauri, if it existed, would be out of conversational reach, but within exchange reach on timescales of single human generations. The comparison with more distant stars makes this concrete. The nearest star after Alpha Centauri is Barnard's star at 5.96 light-years, already a 12-year round-trip delay. Sirius at 8.6 light-years means a 17-year delay. The Pleiades cluster is about 440 light-years away, an 880-year round trip. The center of the galaxy is 26,000 light-years, a 52,000-year round trip. The Andromeda galaxy is 2.5 million light-years, a 5 million-year round trip. In this context, Alpha Centauri occupies a special position in the cosmic communication landscape. It is close enough that information exchange is possible within a human lifetime, impractical as conversation, but feasible as correspondence. No other star system is as close. The next nearest stars are already significantly further. Alpha Centauri is the one stellar system where any communication, were it ever attempted, could receive a response within a generation. This makes the question of whether Alpha Centauri harbours any form of intelligence, however remote and however speculative the possibility, qualitatively different from the same question about more distant stars. The timescale of possible communication is human rather than civilizational. Let us now talk about one of the most scientifically significant recent findings about Proxima Centauri, the detection of Proxima b in 2016, and what that detection has meant for the scientific community and for public understanding of the system. The detection of Proxima b was announced in August 2016 by the European Southern Observatory, based on radial velocity measurements made primarily with the HARPS spectrograph at La Silla Observatory. The lead author was Guillaume Anglada Escudé, and the paper was published in the journal Nature. The announcement attracted extraordinary public and scientific attention. Here was a planet, potentially rocky, with a minimum mass only slightly exceeding Earth's, orbiting in the habitable zone of the nearest star to the Sun. The timing was perfect for public engagement. Exoplanet science had matured to the point where such a finding was credible. The scientific community had a sophisticated framework for discussing habitability, and the proximity to Earth made the finding feel personally relevant in a way that exoplanets around more distant stars do not. The detection was made from radial velocity variations in Proxima Centauri's spectrum with a semi-amplitude of about 1.38 meters per second and a period of 11.186 days. This is an extraordinarily small velocity signal, less than the typical walking speed of a human being expressed as a stellar motion. The measurement required combining many observations over several years and careful statistical treatment to distinguish the planetary signal from the stellar activity noise. The confidence in the detection was high. The statistical significance was reported at roughly 99.9999%, but immediately caveated with the acknowledgement that stellar activity can produce signals that mimic planetary radial velocity variations, and that the confirmation of a planetary nature required ruling out stellar activity as the source. Subsequent observations have been largely consistent with the original detection. Proxima b remains the most credible planet detection at the closest stellar neighbour, and while questions about its exact properties continue to be refined, its existence as a real object is accepted by most astronomers working on the system. What Proxima b is remains substantially uncertain. The minimum mass of 1.07 Earth masses is a lower limit. The true mass could be larger if the planet's orbital plane is inclined relative to our line of sight. If the orbit is significantly inclined, the true mass could be several times Earth's, potentially making Proxima b a sub-Neptune-sized object with a thick, volatile envelope rather than a rocky world like Earth. The orbital period of 11.186 days places it in a regime where tidal locking is almost certainly complete. The tidal forces from Proxima Centauri at this close distance would have synchronized Proxima b's rotation with its orbital period billions of years ago. Proxima b almost certainly keeps one face permanently toward its star and one face permanently away, just as our Moon keeps one face permanently toward Earth. Tidal locking has profound consequences for a planet's climate and habitability. The day side would receive continuous stellar irradiation, potentially hot. The night side would radiate heat into space continuously, potentially very cold. The temperature contrast between the two hemispheres would be extreme in the absence of a substantial atmosphere that can redistribute heat. Whether an atmosphere can survive on Proxima b and redistribute heat sufficiently to make both hemispheres habitable, or at least make the terminator zone habitable, depends on the atmospheric mass and composition, the strength of stellar winds, the presence of a planetary magnetic field, and the detailed history of atmospheric erosion by Proxima's flare activity. These factors are unknown. The theoretical literature on Proxima b's habitability spans a wide range of conclusions, from papers arguing that the combination of tidal locking, flare radiation, and atmospheric erosion makes habitability essentially impossible, to papers arguing that with a sufficiently thick carbon dioxide atmosphere and a strong enough magnetic field, the planet could maintain habitable conditions in the terminator region. The truth is, we do not know, and we cannot determine it from current observations. This is one of the primary motivations for the next generation of observational capabilities. Atmospheric characterization of Proxima b is a tractable scientific goal for instruments that will exist within a decade. Let us now talk about what the discovery of Proxima b meant for the Breakthrough Starshot initiative and for interstellar mission planning more broadly. When Breakthrough Starshot was announced in April 2016, it predated the announcement of Proxima b by about 4 months. The initiative proposed sending laser-pushed light sails to Alpha Centauri, on the grounds that it is the nearest stellar system. The discovery of Proxima b 4 months later provided a specific, identified target, not just the nearest star, but the nearest star with a known, potentially habitable planet. This transformed the scientific case for the mission. Previously, Starshot could only say, we would send spacecraft to the nearest star to learn about it. After Proxima b's discovery, the mission could say, we would send spacecraft to the nearest star to characterize a specific planet in the habitable zone of that star. The trajectory implications of targeting Proxima b specifically, rather than simply the Alpha Centauri system in general, are significant. Proxima is the closest of the 3 stars, and therefore has the shortest transit time for any approaching spacecraft. But Proxima is also separated from Alpha Centauri AB by 13,000 astronomical units. The tiny light sails of Breakthrough Starshot, flying through at 20% of the speed of light, could not easily visit multiple targets within the system. They would need to be aimed specifically at either Proxima or the AB pair. At 20% of the speed of light, the flyby of Proxima b would last on the order of an hour. The spacecraft would need to collect all scientifically useful data: imaging, spectroscopy, magnetic field measurements, charged particle measurements, in roughly the time it takes to watch a movie. The data would then need to be transmitted back to Earth across 4.24 light-years, a transmission that would take 4.24 years at the speed of light. The gram-scale spacecraft would carry a laser communications system capable of transmitting data at very low rates. The imaging resolution achievable by a tiny spacecraft at flyby velocities would be limited. But even low-resolution images of Proxima b, the first direct images of any exoplanet, let alone the nearest potentially habitable one, would be a scientific milestone of the highest order. Whether this mission will ever be built depends on the progression of the underlying technology and the political and financial will to invest in a multi-decade project whose scientific return is distant and uncertain. The current state of the technology is that the required laser power, sail reflectivity, and miniaturized electronics each require multiple orders of magnitude improvement over current capabilities. This is not clearly impossible, but it is also not on any short-term engineering roadmap. The honest assessment is that Breakthrough Starshot, or a mission like it, represents a century-scale engineering project at minimum. The technology readiness levels for each component suggest decades of development, even in an optimistic scenario. Let us now talk about the broader context of Alpha Centauri within the local stellar neighborhood, about the region of space surrounding our solar system and how Alpha Centauri fits into that larger structure. The Sun is located in what astronomers call the local bubble, a roughly spherical region about 300 light-years in diameter that contains unusually hot, low-density gas compared to the average interstellar medium. The local bubble was created by multiple supernova explosions over the past few million years that swept the surrounding gas outward, creating a cavity filled with hot, tenuous plasma. Within this local bubble, the nearest stars to the Sun form what is called the solar neighborhood, the roughly 10 light-year sphere around the Sun, containing the closest stellar systems. This sphere contains approximately a dozen individual star systems, though because most stars are dim red dwarfs, the total number of stars in the neighborhood may be 20 or more. Alpha Centauri is the closest, at 4.24 light-years. Barnard's star is next, at 5.96 light-years, a single red dwarf with no confirmed planets. Wolf 359 is at 7.78 light-years. Lalande 21185 is at 8.29 light-years. Sirius, the brightest star in the night sky, is at 8.58 light-years. WISE 0855-0714, a controversial cold brown dwarf, is at roughly 7.18 light-years. These are the immediate stellar neighbours of our Sun. What this neighbourhood reveals is how sparse the stellar distribution is in our region of the galaxy. The average separation between stars in the solar neighbourhood is roughly 5 to 7 light-years. This is an almost unimaginable volume of empty space between each star system. Billions of cubic astronomical units of vacuum separating each stellar oasis from the next. The galaxy contains roughly 200 to 400 billion stars, but the galaxy is also enormous, a disk roughly 100,000 light-years in diameter and a few thousand light-years thick. The density of stars varies enormously, from the dense central bulge to the sparse outer disk. In our region, the inner edge of the Orion Arm, about 26,000 light-years from the galactic center, the stellar density is relatively modest. Alpha Centauri's triple-star architecture is not unusual for the solar neighborhood. Roughly half of Sun-like stars are in binary or multiple star systems. The Alpha Centauri AB binary with distant Proxima companion is a common configuration. The exact fractions vary depending on stellar mass and definition, but multiple star systems are as common as single stars among Sun-like stars. This means that if the Alpha Centauri AB system has planets in its habitable zone, that would suggest that binary star systems, which represent roughly half of all potential planetary hosts, are viable environments for Earth-like planets. Conversely, if the binary nature of the AB pair has suppressed planet formation or orbital stability in the habitable zone, it would suggest that binary stars may be less common habitable planet hosts than single stars. The answer to whether Alpha Centauri AB has habitable zone planets therefore has implications not just for this one system, but for the general question of how many of the roughly 100 billion stars in our galaxy might host habitable planets. The stakes of the search are higher than they might appear. Let us now talk about one more aspect of the Alpha Centauri system that is scientifically significant and rarely discussed in popular treatments: the metallicity of the stars and what it implies for any planets in the system. Metallicity in astronomy refers to the abundance of elements heavier than hydrogen and helium in a star, what astronomers somewhat misleadingly call metals, meaning all elements beyond helium, regardless of whether they are actually metallic in the chemical sense. Metallicity is measured relative to the Sun and expressed logarithmically. A star with solar metallicity has the same heavy element abundance as the Sun, while a star with negative metallicity has fewer heavy elements. The metallicity of a star reflects the chemical composition of the gas cloud from which it formed. Stars that formed earlier in the galaxy's history tend to have lower metallicity because fewer heavy elements had been produced by stellar nucleosynthesis at that time. Stars that formed more recently, from gas enriched by billions of years of supernova explosions and stellar mass loss, tend to have higher metallicity. Alpha Centauri A and B are slightly metal-rich compared to the Sun. Their iron abundance is roughly 50% higher than the Sun's, a significant enrichment. This means they formed from a gas cloud that was more chemically enriched than the gas that formed our Sun, suggesting either that they formed later or from gas in a more chemically evolved region of the galaxy. Higher metallicity in the host star correlates with higher likelihood of giant planet formation. This is one of the strongest statistical patterns in exoplanet research. Giant planets are preferentially found around metal-rich stars. The correlation is less clear for rocky planets, but the raw material for rocky planet formation, silicates, iron, other heavy elements, is more abundant in higher metallicity systems. The higher metallicity of Alpha Centauri A and B is therefore mildly positive evidence for the presence of planets. Not conclusive, individual systems deviate from statistical trends, but statistically consistent with having more planetary building material than average. Proxima Centauri appears to have similar metallicity to the AB pair, consistent with a common origin in the same molecular cloud. The planet Proxima b, if it is indeed rocky, could be expected to be chemically enriched in heavy elements compared to Earth. More iron, more silicates, more of the building blocks of a rocky world. Whether this enrichment affects its internal structure, its volcanism, its magnetic field generation, or its potential habitability in significant ways is uncertain. This is one of many threads of the Alpha Centauri story that connects local observations to broader questions about the conditions for life in the galaxy. The chemical enrichment of the system, its triple-star architecture, the tidal locking of Proxima b, the flare activity of Proxima Centauri, the orbital stability constraints imposed by the AB binary. All of these interacting factors determine whether the nearest stellar system to the Sun is a place where life could exist or has existed. We do not know the answer. The observations needed to answer it are in progress or in planning. The instruments needed for the most decisive measurements are under construction or in concept development. Within a decade, perhaps two, we will know more about the Alpha Centauri system than all of human history before this generation has revealed. The stars that Galileo observed with his first telescopes, that Henderson measured the distance to in the 19th century, that science fiction writers have imagined as humanity's first interstellar destination for a century, those stars are now the subject of the most sophisticated observational programs ever applied to any stellar target. We are learning about our nearest neighbours in the cosmos at a pace that was impossible even a generation ago. And what we learn, whether those stars have Earth-like planets, whether those planets have atmospheres, whether those atmospheres hint at chemistry consistent with life, will be some of the most significant scientific knowledge humanity has ever acquired. Because it will be knowledge about whether the nearest possible place beyond our solar system could be inhabited. The triple star system, 4.24 light-years away, is not an abstraction. It is a place. With physics, with chemistry, with orbital mechanics, with stellar evolution, with possibly planets, and possibly atmospheres, and possibly, conditions where something lives. We are looking at it right now in the southern sky with every instrument we can bring to bear. Let us talk about something that connects the Alpha Centauri system to the deeper history of the galaxy, about where these three stars came from and what their origin tells us about the chemical and dynamical history of our region of the Milky Way. Stars do not form in isolation. They form in molecular clouds, enormous concentrations of cold gas and dust that collapse under gravity to produce clusters of hundreds or thousands of stars simultaneously. The Sun almost certainly formed in such a cluster roughly 4.6 billion years ago, though the cluster has long since dispersed as the member stars drifted apart over billions of years of orbital motion around the galactic center. Alpha Centauri A, B, and possibly Proxima were likely born in the same or a nearby molecular cloud. Their similar metallicities, all three stars having roughly comparable heavy element abundances, support a common or closely related origin. Stars that form from the same molecular cloud share essentially the same chemical composition because they condense from the same well-mixed gas. The age of the Alpha Centauri A-B system has been estimated at approximately 4.85 billion years, slightly older than our solar system's 4.6 billion years. This is consistent with a common origin region. Both the Sun and Alpha Centauri formed in the same broad epoch of star formation in this part of the galaxy, from gas with similar chemical enrichment around the same time in galactic history. This means that while the Sun and Alpha Centauri were not born from precisely the same molecular cloud, the Sun's birth cluster has been identified as likely originating from a different region of the galaxy. They share a broadly common cosmic heritage. Both formed in the same galactic era. Both formed from gas that had been through roughly the same number of cycles of stellar birth, nuclear synthesis, and stellar death. Both represent the same generation of galactic chemical evolution. The implication is that any planets around Alpha Centauri, particularly any rocky planets, would be built from similar raw materials as the planets of our solar system, the same elements in broadly similar proportions. If Earth-like rocky worlds can form around the Sun, the chemical preconditions for similar worlds to form around Alpha Centauri A and B are present. This is not a guarantee. The dynamical environment matters, the binary nature of the A-B system, the close companion, the gravitational perturbations that potentially suppress or alter planet formation in ways we discussed. But chemically, the building blocks are there. Let us now talk about what the binary orbit of Alpha Centauri A and B means for anyone observing the system over human timescales. Because the 79.9-year orbital period is short enough that it is observable, and the changes in the system over a human lifetime are measurable. In the year 1955, Alpha Centauri A and B were at their maximum separation, A pastron, with roughly 35.6 astronomical units between them and an angular separation on the sky of approximately 22 arcseconds. This would have made them the easiest they get to separate visually, looking like a wide and obviously double star, even at low magnification. In 2035 to 2036, they will reach periastron, minimum separation, with roughly 11.2 astronomical units between them, and an angular separation on the sky of only about 2 arcseconds. At 2 arcseconds separation, a good-sized amateur telescope is still capable of resolving them, but the split becomes tighter and more challenging. Currently, in 2024, the separation is approximately 5 to 6 arcseconds and decreasing as the binary approaches periastron. Someone who observed Alpha Centauri in 1970 and observes it again in 2024 would notice the pair has visibly closed. The two stars appear noticeably closer together than they did half a century ago. This observable change over a human lifetime is one of the most direct demonstrations available in amateur astronomy of stellar orbital dynamics. You can watch stars move, not metaphorically or through data analysis, but literally. Compare observations separated by decades and see the geometry change. The Alpha Centauri binary is the best example of this, accessible to observers in the southern hemisphere. After periastron, in the mid-2030s, the separation will begin increasing again. By the 2090s, it will be approaching apastron again. A person observing now who is in their 30s could potentially observe the full periastron and then watch the pair widen again through most of their remaining life. This human-scale observability of the orbital dynamics connects the abstract physics of binary star mechanics to direct personal experience in a way that most astronomical phenomena do not permit. The orbital period of 79.9 years is just short enough that a long-lived person can observe a full cycle, or at least the majority of one, while most astronomical processes are either so fast they require high-speed instruments, or so slow they span geological timescales. Let us now talk about how the Alpha Centauri system is viewed in the context of the search for extraterrestrial intelligence. What SETI programs have done and are doing with respect to this nearest stellar system. SETI programs have been ongoing in various forms since Frank Drake's Project Ozma in 1960, which aimed radio telescopes at Tau Ceti and Epsilon Eridani, two nearby Sun-like stars. Drake chose these two stars because they were nearby, they were single stars similar to the Sun, and they were in the right mass range to potentially have habitable planets. Alpha Centauri, despite being the nearest star system, was not the initial focus of many early SETI programs, partly because it is visible only from the southern hemisphere, and most of the early major radio telescopes were in the northern hemisphere, and partly because its binary nature was considered a complication. As SETI programs have matured and as southern hemisphere radio facilities have expanded, Alpha Centauri has received increasing attention. The Parkes Radio Telescope in Australia, one of the most significant radio telescopes in the southern hemisphere, has been used in SETI programs targeting the Alpha Centauri system. In 2020, the Parkes telescope detected an unusual narrowband radio signal from the direction of Proxima Centauri, designated BLC1, Breakthrough Listen Candidate 1. The signal was in the 982 to 983 MHz range, a frequency at which natural astrophysical processes do not typically produce narrowband emissions. It appeared to shift in frequency over time, in a way consistent with the Doppler shifting expected from a transmitter on a planet orbiting Proxima. This detection generated significant internal discussion within the Breakthrough Listen program before being reported publicly. When finally reported in 2020 and 2021, it was accompanied by the assessment that the signal is almost certainly of human origin, terrestrial or satellite interference, rather than extraterrestrial. The signal appeared only in one of the polarizations of the receiver, was not confirmed in subsequent observations, and exhibited characteristics consistent with radio frequency interference rather than an intentional extraterrestrial transmission. No credible SETI candidate signal has ever been confirmed from any source. The BLC-1 signal from Proxima Centauri direction follows this pattern, interesting enough to investigate seriously, but ultimately not surviving careful scrutiny as an extraterrestrial origin candidate. The episode is nevertheless instructive. It demonstrates that the Alpha Centauri system, and specifically Proxima Centauri with its potentially habitable planet, is the highest priority target for SETI programs. Any signal from that direction will receive extraordinary scrutiny. And the fact that a signal was detected, investigated seriously, and then determined to be terrestrial interference, rather than never being detected at all, shows that the sensitivity of current instruments is sufficient to detect certain classes of signals from that distance. What are the realistic prospects for detecting a genuine signal from Alpha Centauri, if any technological civilization were transmitting from there? A civilization broadcasting at the power level of our current strongest deliberate transmissions, the Arecibo message sent in 1974, could not be detected at Alpha Centauri's distance with any current instrument. The Arecibo message was deliberately targeted at a dense star cluster tens of thousands of light-years away. Detecting an equivalent signal at 4.24 light-years would require sensitivity far beyond current capabilities. However, a civilization deliberately targeting us with a powerful, focused transmission, analogous to the difference between a lighthouse and a searchlight, could potentially be detected at Alpha Centauri distances with current radiotelescope sensitivity. The question is not only whether the technology exists to transmit, but whether any civilization would choose to aim a powerful signal specifically toward the Sun. The nearest star is the most obvious target for any mutual awareness program. If there were a technological civilization around Proxima Centauri, they would know exactly where the Sun is. They can see it as a bright star in their sky. They would know its spectral type and approximate age. They would know it is a G-type main sequence star in the right mass range to potentially have habitable planets. Whether any such civilization exists, whether they know about us, and whether they would choose to signal in our direction, these are questions that the current state of knowledge does not allow us to answer. SETI remains an empirical science, awaiting its first confirmed positive result. What is clear is that Alpha Centauri, and particularly Proxima Centauri, with its confirmed planet in the habitable zone, is where the SETI community will be pointing its most sensitive instruments for the foreseeable future. Let us now talk about something more philosophical, about what the existence of the Alpha Centauri system at 4.24 light-years means for the human sense of scale and for our relationship with the cosmos. Human beings evolved in environments where the relevant scales were kilometers, the distance to the next water source, the distance a predator could cover in minutes, the distance across a territory. Our intuitions about distance are calibrated to these scales. Larger distances, the size of continents, the circumference of the Earth, require intellectual effort to grasp, but remain within a range where analogy and experience can help. The distance to the Moon, 384,000 kilometers, is the first scale at which direct human experience provides no intuitive guidance. It is large compared to anything on Earth's surface, yet we have sent people there. The distance to the Sun, 150 million kilometers, is 390 times further. The distance to the nearest star, 40 trillion kilometers, is 270,000 times further still than the Sun. No analogy fully captures this. The standard one, if the Sun were a grapefruit in your hand, Proxima Centauri would be another grapefruit 17 kilometers away, is instructive, but ultimately still too small a scale for intuition to operate normally. We do not navigate cities in which 17-kilometer separations between objects represent the nearest neighbor distance. The analogy helps, but does not resolve the scale problem. What Alpha Centauri's distance fundamentally communicates, if you sit with it honestly, is the isolation of our solar system. The nearest star is so far away that the fastest vehicles humans have ever built would require more than 6,000 years to reach it. Any information we send travels at the speed of light and takes 4.24 years. Any physical object we send moves slower than light and takes much longer. We are alone in our solar system, in a very physical sense. The nearest alternative stellar environment is across a gulf so large that it takes light itself years to cross. The stars visible in the night sky, even the nearest ones, are not neighbors in any operational sense. They are distant objects that can only be reached by light, and perhaps by certain theoretical propulsion concepts that remain engineering fantasies. This is not a pessimistic conclusion, it is an honest one, and it makes the achievements of the astronomers and physicists who have characterized Alpha Centauri, measured its distance, identified its triple star nature, discovered a planet around Proxima, begun the search for planets around A and B, all the more remarkable. We cannot go there. We can barely send signals there. But we have learned an enormous amount about what is there using instruments at our solar system's edge, interpreting photons that traveled 4.24 years to reach us. This is what astronomy is at its deepest level, the ability to learn about places we cannot go through the information carried by light, using physics and mathematics to decode what that light tells us. Alpha Centauri is the clearest case of this in practice, the nearest stellar system characterized in extraordinary detail despite being unreachable by any current or near-future technology. Let us now talk about what might become possible in the long-term future, about the trajectory of human technological capability and what it implies for Alpha Centauri over centuries rather than decades. The history of technology is not a simple extrapolation of current trends. Major discontinuities, transformative technologies that change the landscape of what is possible, occur irregularly and are not predictable from the outside. No one in 1850 predicted radio. No one in 1900 predicted nuclear power. No one in 1950 predicted the internet. Any prediction about what humans might achieve in the next century or two regarding interstellar travel therefore carries enormous uncertainty. It might be true that current physics sets hard limits, that without some method of faster-than-light travel, which appears forbidden by general relativity, any journey to Alpha Centauri requires decades at minimum, and the journey times of any crewed mission are measured in generations. But within the constraints of physics as we understand it, there is significant room between what we can do now and what might be achievable with advanced technology. Nuclear pulse propulsion, using a series of nuclear explosions to propel a large spacecraft, could potentially accelerate a vessel to a few % of the speed of light, cutting the transit time to Alpha Centauri to a few centuries. Fusion propulsion, if it becomes practical at scale, could do better. Advanced laser sail concepts could potentially reach the timescales of breakthrough starshot, decades for robotic probes. Each of these technologies faces enormous engineering challenges. Nuclear pulse propulsion was studied seriously in the 1950s and 1960s, the Orion project, and was technically feasible in principle, but politically blocked by the Partial Nuclear Test Ban Treaty. Fusion propulsion requires sustained fusion reactions at densities and temperatures not yet achieved continuously in any laboratory. Laser arrays at the power levels required for starshot do not exist, and would represent the largest engineering projects in human history. But none of these is clearly physically impossible. They face engineering challenges rather than fundamental physics barriers. A civilization with the resources, the motivation, and the engineering capabilities of humanity a century or two hence might be able to address these challenges. The question is not primarily technical, but motivational and civilizational. Interstellar missions are multi-generational. A crewed mission, even at 10% of the speed of light, achievable in principle with very advanced propulsion, would take 42 years to reach Alpha Centauri. The crew that departed would be elderly or dead by arrival. Children born on the ship would be the ones to complete the journey. The support infrastructure on Earth would need to maintain the mission across multiple human generations. This requires a stability of institutional purpose and a continuity of civilization that is difficult to guarantee on human political timescales. It requires the mission to be valued not by the generation that launches it, but by the generations that come after, who may have different priorities and different values. These are the real constraints on interstellar travel, not primarily the physics, but the sociology and the political economy. Alpha Centauri will remain unreachable until and unless human civilization develops the institutional capacity for multi-generational projects of unprecedented scale. Whether that capacity develops, whether humanity becomes the kind of civilization that can sustain such projects, is one of the most important open questions about the long-term future of our species. Let us now talk about the specifically visual experience of Alpha Centauri, about what it looks like through different instruments and what each level of observation reveals. To the naked eye, from the southern hemisphere on a clear night, Alpha Centauri appears as the third brightest star in the night sky. It sits in the constellation Centaurus, near the prominent Southern Cross. Its apparent magnitude is roughly -0.29, brighter than any star except Sirius and Canopus. It is distinctly bright, obviously brighter than the surrounding stars, drawing the eye. To the naked eye, Alpha Centauri appears as a single point. The two components of the AB binary, currently about 5 arc-seconds apart, are far too close together for the unaided human eye to separate them. The human eye can at best resolve features separated by about 60 arc-seconds under optimal conditions. At 5 arc-seconds, the two stars merge into a single, brilliant point. Through binoculars, even modest 7x50 or 10x50 binoculars, Alpha Centauri still appears as a single point. The resolution of binoculars at typical magnifications is not sufficient to split a pair separated by 5 arc-seconds. Through a small telescope, a 60 or 70 millimeter refractor at 50 times magnification, the two stars begin to be separable. At 5 arc-seconds and the focal lengths of typical small refractors, the pair is clean, bright stellar disks, separated by a visible gap, one slightly warmer white, the other slightly more yellow or orange. The color difference subtle but perceptible in a quality instrument under steady skies. This is one of the most beautiful double-star views in the southern sky. Two brilliant stellar companions separated by a gap that represents the distance from the Sun to Saturn. Through a larger telescope, 150 to 200 millimeters aperture, the pair is split easily, even at moderate magnification. the color difference becomes more apparent. At high magnification, the airy disk diffraction pattern of each star, the bright central dot surrounded by concentric diffraction rings, is visible, and the gap between the two stars is unmistakable. This is a showpiece object for Southern Hemisphere observers and astronomers. Through a professional telescope, the kind of instrument capable of arcsecond or sub-arcsecond astrometry, the two stars can be measured with sufficient precision to track their orbital motion over time. Comparing positions measured years apart reveals the curvature of the orbit, the changing separation, the changing position angle. The binary dynamics become directly visible as a geometric fact rather than an inferred one. Proxima Centauri in any amateur telescope appears as a faint reddish point, a magnitude 11.1 object requiring at least 100 mm of aperture and knowledge of its precise location to distinguish from surrounding field stars. Its red color, the color of a cool M-dwarf surface at approximately 3000 Kelvin, is subtly but distinctly visible in instruments of sufficient aperture under good conditions. Knowing that this faint reddish point is the closest individual star to the Sun gives it a significance that its visual appearance entirely fails to suggest. Through an infrared detector, Proxima brightens considerably relative to background stars. Red dwarfs emit a much larger fraction of their energy in the near-infrared than in visible light. In infrared images, Proxima is a comparatively bright object. Its thermal emission at wavelengths around 1 to 2 microns is much more substantial than its visible output. Infrared observations of Proxima have revealed its flaring behavior more clearly and have contributed to characterizing its activity cycle. Through X-ray telescopes, orbital X-ray observatories like Chandra and XMM Newton, Proxima is a dynamic source. Its frequent flares produce intense X-ray bursts that are far brighter than the quiescent emission, revealing the violent magnetic activity of this seemingly quiet, dim star. An X-ray image of Proxima during a major flare shows it dramatically brightening, a visual demonstration of why Proxima B's habitability is uncertain despite its position in the nominal habitable zone. The multiple levels of observation of Alpha Centauri, from naked eye to binoculars to small telescope to professional instruments to X-ray satellites, each reveal different aspects of the system that are invisible at other wavelengths and resolutions. This layered observability makes the system an instructive example of how astronomy works. Each new tool, each new wavelength, each new level of sensitivity reveals aspects of reality that were there all along, but invisible to previous instruments. Let us now talk about one of the most profound implications of the Alpha Centauri system for the long-term future of humanity, about what the existence of 3 stars with potentially habitable planets at the nearest stellar distance means for the concept of humanity as a multi-stellar species. We have discussed the enormous challenges of interstellar travel, the distances, the energy requirements, the travel times, the engineering demands. These are real, and they are not going to be overcome in the next generation or perhaps the next several generations. But the fact that they are real challenges rather than absolute impossibilities means that on a civilizational timescale, centuries to millennia, they might be overcome. Not certainly, not even probably given our current trajectory, but possibly. If they are overcome, if humanity does eventually develop the technology to send probes or people or autonomous machines to Alpha Centauri, then the triple star system will become the first node of any interstellar network that humanity might eventually build. Not because Alpha Centauri is the most interesting stellar system, not because it has the most promising habitable planets, but because it is closest. And in a universe where the speed of light is the ultimate speed limit, closeness is an irreducible advantage. Every communication round trip to Alpha Centauri takes 8.5 years. To Barnard's star, it takes 12 years. To Sirius, it takes 17 years. The difference is significant. It determines the timescale of any coordination, any exchange of information, any sense of connection between the solar system and the nearest outpost. Alpha Centauri, if humanity ever establishes any presence there, would be the node closest to home in any interstellar network, the one where the light-speed communication delay is minimized, the one where a message sent from Earth arrives first. Whatever it turns out to contain, whether its stars have habitable planets, whether those planets harbor life, whether any of those planets could be transformed into human habitations, it will be the first destination of any genuine interstellar civilization. This makes the scientific understanding of Alpha Centauri, the characterization of its planets, the measurement of its stellar environments, the determination of whether it contains habitable conditions, more than just academic curiosity. It is reconnaissance. The most advanced reconnaissance we can do from Earth of the place that will matter most to any future that extends humanity beyond the solar system. We are doing that reconnaissance now. The instruments are being built. The observations are being accumulated. The data is flowing. Every photon collected from Alpha Centauri by every telescope on Earth and in orbit is a small piece of that reconnaissance. Every measurement of the radial velocity of Alpha Centauri A and B is a step toward knowing whether Earth-like planets orbit those suns. Every observation of Proxima b contributes to understanding whether the nearest confirmed exoplanet might harbour life. This is the context in which the scientific study of Alpha Centauri should be understood. Not just a nearby interesting stellar system, the frontier of human knowledge about our immediate cosmic neighbourhood. The target of the most detailed planetary search program ever applied to any stellar target other than our own Sun. Possibly the location of the first extrasolar worlds ever confirmed to have atmospheres. Possibly the first place beyond our solar system ever confirmed to harbour any form of life. Possibly none of these things. The planets may be barren, the atmospheres thin or absent, the chemistry sterile. But the question is worth asking. The instruments are becoming capable of asking it, and the answer, whatever it is, will be one of the most significant pieces of knowledge humanity has ever acquired about the cosmos it inhabits. Let us now talk about the specific sense in which 3 stars are more interesting than 1, about what the triple architecture of the system adds scientifically that a single star would not. A single star with planets, like our Sun, provides one sample of planet formation under specific conditions. A triple star system provides multiple experiments running simultaneously under related but different conditions. The planets forming around Alpha Centauri A, if they exist, formed in the gravitational field of a G-type star with a K-type companion at a varying distance of 11 to 36 astronomical units. The tidal perturbation from the companion has affected the disk dynamics. The companion's radiation has added to the total flux in the system's early history. The outcome, if planets exist, represents planet formation in a gravitational and radiative environment quite different from our solar systems. The planets forming around Alpha Centauri b, if they exist, formed in the gravitational field of a K-type star with a G-type companion. Different stellar mass means different disk temperature, different snowline location, different dominant chemistry in the disk, different disk evolution timescale, different outcome potentially from either the A system or our solar system. The planet around Proxima Centauri, the confirmed Proxima b, and potentially others, formed in the gravitational field of a flare-active M dwarf with no close companion. The disk was cooler, more compact, evolved more slowly, was irradiated with a very different ultraviolet and X-ray spectrum. The outcome is clearly different, a planet much closer to its star than any in our solar system, likely tidally locked in an environment shaped by stellar flares. 3 stars, 3 different stellar types, 3 different planet formation environments, 3 different potential outcomes, all at the same distance from the Sun, all accessible to the same observations, all part of the same gravitational system. The Alpha Centauri triple system is a natural laboratory for comparative planetology, the study of how planet formation varies with stellar conditions. No single star system provides this comparison. Alpha Centauri provides 3 simultaneous experiments in planet formation, all observable at the same distance, all with the chemical and dynamical heritage of the same stellar birth region. This comparative richness is one of the system's greatest scientific values. Not just the nearest stars, the nearest natural experiment in the diversity of planetary systems. Let us now talk about what is perhaps the most haunting aspect of the Alpha Centauri system, the question of whether anything has been looking back at us from there. Our Sun is visible from Alpha Centauri as a star of approximately magnitude 0.5, one of the brightest stars in its sky. A civilization around Alpha Centauri A or B would see our Sun as a bright, yellowish star in their sky, near the constellation they might call Cassiopeia from our perspective, but which would look different from their vantage point. They would have been able to see our Sun since long before the Earth formed. For 4.6 billion years, the Sun has been shining in the sky of any planet around Alpha Centauri. For the last several hundred million years, since the Cambrian explosion, when complex multicellular life first proliferated on Earth, Earth has been in the photosphere of that distant star from Alpha Centauri's perspective, too small and too dim to detect with any instrument short of the most advanced technological capability. A civilization around Alpha Centauri that developed the equivalent of our current technology and wanted to study the nearby Sun-like star could potentially detect Earth's existence. Earth transits the Sun, from Alpha Centauri's perspective, approximately once per year, causing a tiny dimming of the Sun's light. Whether this dimming falls in the right geometry to be detectable from Alpha Centauri depends on the orbital plane alignment. The probability of Earth's orbit being edge-on enough to produce detectable transits as seen from Alpha Centauri is roughly 1 in 215. A long shot, but not zero. More practically, a civilization with advanced spectroscopic instruments could, in principle, detect the spectral signatures of Earth's atmosphere in the reflected light of a planet orbiting the Sun, the oxygen, ozone, water vapor, and methane that constitute Earth's biosignatures. Whether this detection would be feasible with any conceivable current technology is uncertain. It would require instruments far beyond what we have. But it is not clearly impossible for a civilization at our technological level or somewhat beyond it. This means that if there is anyone around Alpha Centauri with our level of technology or better, and if they are looking for planets around nearby stars the way we are looking for planets around Alpha Centauri, they might, just might, know that Earth exists. They might even know that Earth has a remarkable atmosphere full of biologically produced gases. This is speculation layered on speculation. But it is honest speculation grounded in the physics of detection. and it gives the distance between our two solar systems a reciprocal quality. We are learning about them from 4.24 light-years away, and in principle, they could be learning about us from the same distance. The light that left our Sun 4.24 years ago is arriving at Alpha Centauri right now. It carries in its spectrum the reflected light of Earth, a pale blue dot orbiting our star, tiny and almost certainly undetectable, but present. Our planet's light is in that spectrum, arriving at a stellar system whose planets we are now beginning to characterize. Whether anyone is there to receive it is the question that the next generation of telescopes may begin to answer. Let us now talk about what a definitive detection of a habitable planet around Alpha Centauri A or B would mean, not just scientifically, but for the long-term trajectory of human civilization. The confirmation of an Earth-like planet in the habitable zone of one of the Alpha Centauri stars, with a detectable atmosphere containing water vapor and potentially other biosignature gases, would immediately transform interstellar travel from an abstract, long-term aspiration into a specific, defined goal. Not someday we might go to the stars, but there is a specific world with a specific set of measured properties at a specific distance that we can characterize in increasingly fine detail. The difference between an abstract aspiration and a specific goal is enormous for motivating and sustaining a civilizational project. The Apollo program was not inspired by the general idea of going into space. It was motivated by the specific goal of landing on the moon, a specific object by a specific date. The specificity of the goal made the resource mobilization, the institutional commitment, and the sustained focus possible. A confirmed Earth-like planet at Alpha Centauri. A world with surface conditions compatible with life, with an atmosphere we can study from Earth, with properties we can measure with increasing precision over decades, would be that kind of specific goal. Not go to the stars, but go to that world, that one visible even now in the night sky. That one whose light we have analyzed and whose atmosphere we have characterized. That specific place. The civilization-scale motivation to eventually reach such a world would be qualitatively different from the motivation to reach an abstract interstellar destination. The political sustainability of a multi-generational project is dramatically enhanced when the goal is concrete and the target is known. This is why the planetary search programs focused on Alpha Centauri are not merely academic exercises. They are potentially the first step in a sequence of events that could eventually, centuries from now, result in the first physical human contact with another stellar system. The first photon collected by a telescope of a planet in Alpha Centauri's habitable zone is a link in a chain that might ultimately connect to a ship sailing through that system. We do not know if such a planet exists. We do not know if it is habitable. We do not know if it harbors life. We do not know if humanity will survive long enough and maintain the civilization's coherence and values long enough to eventually reach it. But we are looking, with increasingly capable instruments, with increasing scientific rigor, with increasing precision, and every measurement brings us closer to knowing what is there, to knowing whether the nearest stellar system to our Sun is a place of barren rocks and sterilizing flares, or a place of warm worlds with liquid oceans and perhaps, possibly, improbably, life. The answer is in those stars. The light from the answer is traveling to us at the speed of light right now. We are building the instruments to read what that light carries, and the story of what we find will be one of the most significant chapters in the history of the human species. Whether it ends in discovery or in the profound understanding that the universe is more empty and more barren than our most optimistic hopes suggested. Alpha Centauri is 3 stars at 4.24 light-years. It changes everything about how we think about our stellar neighborhood, about the architecture of nearby planetary systems, about the prospects for life beyond Earth, about the long-term future of humanity in this galaxy. 3 stars, changing everything. Go outside tonight and look south. If you are in the southern hemisphere, or in the southern United States, or anywhere south of roughly 30 degrees north latitude, find the Southern Cross first. It is unmistakable. 4 bright stars in a compact cross shape, one of the most distinctive patterns in the southern sky. Then look slightly to the upper left of the Southern Cross toward the bright star Hadar, Beta Centauri, and just beyond it you will find the brightest star in that part of the sky. That is Alpha Centauri, 3rd brightest star in the entire night sky, a brilliant, steady point, not twinkling as much as the stars around it because it is so bright and so close. Slightly yellowish compared to the blue-white stars nearby. It looks like one star. It is 3. Here is what is actually there. 2 solar-type stars, Alpha Centauri A and B, orbiting each other on an 80-year ellipse. Right now, in 2024, they are closer to each other than they have been in decades, approaching their minimum separation, which occurs around 2035. At their closest, they are separated by the distance from the Sun to Saturn. At their farthest, by the distance from the Sun to Neptune. 2 suns circling each other over and over for billions of years. And at a distance so enormous it is almost meaningless to express. 13,000 astronomical units from the AB pair, about 2 trillion kilometers. A 3rd star. Proxima Centauri, a tiny red dwarf, invisible to the naked eye, currently the closest individual star to the Sun, at 4.24 light-years, orbiting its 2 larger companions once every 550,000 years. The light from Proxima Centauri entering your eyes left that star 4.24 years ago. When that light departed, it was 2019 or 2020 on Earth. Whatever is happening around Proxima right now, whatever is occurring on Proxima b, the planet confirmed in 2016, orbiting in Proxima's habitable zone, we will not know about it for another 4 years at minimum. We cannot reach Alpha Centauri. The fastest spacecraft ever built would take more than 6,000 years. A signal sent at the speed of light, the absolute maximum possible, takes 4.24 years to arrive, and any response takes 4.24 years to return. The minimum round-trip communication time is 8.5 years. This is not an engineering limitation, it is physics. And yet we know an extraordinary amount about what is there. Alpha Centauri A, slightly larger and brighter than our Sun, the closest thing to a solar twin in the cosmos, with gravity that has shaped planet formation in its surrounding disk for 4.85 billion years. Alpha Centauri B, slightly smaller and cooler, an excellent stellar host for habitable planets in its own right, currently being monitored by the most precise spectrographs ever built for the gravitational whisper of an Earth-sized world in its habitable zone. Proxima Centauri, dim and red and ancient future, with 4 trillion years of hydrogen fuel remaining, host to at least one planet, Proxima b, a world of roughly Earth's mass, orbiting in the zone where liquid water could exist, tidally locked so one face always looks toward its star, bombarded by stellar flares, its atmospheric fate unknown and under intense scientific investigation. We know all of this from here, from instruments on Earth and in orbit, collecting photons that travelled 4.24 years across the void, decoding what those photons carry, building up a picture of 3 stars and their worlds without ever going there, without ever touching anything in that system, without sending so much as a radio signal that has yet had time to arrive. This is what astronomy is at its most profound. The universe is unreachable. The distances are incomprehensible.
And yet knowledge crosses those distances in the form of light, and patient instruments and careful mathematics decode that light into real physical understanding of real physical places. The 3 stars of Alpha Centauri are the nearest experiment nature has run in the vicinity of our own solar system. 3 different stellar environments, a G dwarf, a K dwarf, an M dwarf, all at the same distance from Earth, all part of the same gravitational family, all potentially hosting planets, all available for study with increasing precision as our instruments improve. Within the next decade, we may know whether Alpha Centauri A or B has Earth-sized planets in habitable zones. Within the next 2 decades, we may know whether Proxima B has an atmosphere. Within the next century, we may know whether any of those atmospheres carry the chemical signatures of life.
And someday, not soon, perhaps not for centuries, perhaps not for millennia, the most ambitious civilization in the history of life on Earth may aim the most ambitious technology ever built toward that bright point in the southern sky and begin the long crossing. 4.24 light years, 3 stars, possibly worlds, possibly life. Certainly the most important stellar address in the cosmos for the species now looking up at them from a planet orbiting the Sun. Look at that bright point tonight. Hold in your mind what it actually is. Not a star. 3